Okay, welcome back. In this lecture, we are going to look at the concepts of global alignment and semi-global alignment. We closed the last lecture by looking at the motivation for approximate sequence matching. We looked at the definition of sequence alignment, alignment cost and edit distance, and we realized that these type of problems can be solved using dynamic programming. So, we developed a dynamic programming algorithm to compute an alignment that required minimum number of edit operations. So, extending this lecture further, let us recall the definitions from the last lecture that we will be using in this lecture as well. So, recall that in the sequence alignment we had two sequences as input A and B. So, you have two sequences, and the way we defined alignment of A and B was using two sequences U and L, right. So, these sequences U and L will be built on alphabet sigma, plus they will have an additional special character dash symbol. So, these U and L have properties such that if you remove dash symbol from U, then you get back sequence A. Similarly, if you remove dash characters from sequence L, then you get back B, sequence B. So, in other words, we are forming these sequences U and L by inserting dash characters in A and B respectively, and both of these sequences U and L are of equal length. Now, once we gave this definition of alignment, we realized that under this definition many alignments are possible. So, for example, if we take sequences A and B as ELV and VIS, then you can see that there are many alignments possible that satisfy the constraints that we defined, that all these U and L are of equal length, and all of them, if you see, A is a subsequence of U and B is a subsequence of L. So, this property is being satisfied in all these alignments. Therefore, we needed a method to quantify how good an alignment is, and for that we gave a cost model. So, the simplest cost model that we could think of is a unit cost model, in which we think of each match as a cost 0 and everything else, for example, a mismatch or aligning against a gap symbol would cost 1. So, these correspond to the edits of mismatch, insertion or deletion, whereas this involves no edit. So, therefore, we were costing this as 0. Now, under this alignment cost model, we can give the cost to the entire alignment by basically looking at the individual columns of the alignment and measuring comparing the two characters and seeing basically whether the characters are matching, mismatching, or whether the dash symbol is involved or not. So, for example, in this case this alignment has cost 3 because of a mismatch and 2, so 1 insertion and 1 deletion. So, therefore, this alignment cost is necessary to define how good alignment is. Now, under this cost model we were able to come up with the optimization function, where we said that under this cost model I am looking for the alignment with minimum cost. So, we also realized that this is equivalent to solving the edit distance problem, because we are looking for an alignment which gives us minimum number of edit operations for converting A to B, right. So, given this formulation, we came up with a quality time algorithm to solve this problem. So, in the first step we solved for the edit distance D, and then once we had the edit distance, using a trace back we solved for the alignment as well. So, the recurrence was done using dynamic programming technique. So, we realized that the alignment of sequence A and B, we can define a sub problem which is much simpler to solve. So, in the sub problem we are aligning prefix of A versus prefix of B, and because the alignment between these two strings can only end with 3 possibilities, that is a mismatch or a insertion on character sequence A or insertion on sequence B. So, because there are only 3 possibilities, we defined the recurrence considering those 3 possibilities and solve the DP table. Now, because this DP table is of size m cross n and each cell takes order 1 time, we were able to solve this dynamic programming in order mn time, and a simple trace back in this dynamic programming also gives you back the alignment. So, this was a quick recap of the last lecture. In this lecture, we are going to extend these ideas further. At the first step we are going to see a switch from alignment cost to alignment score. I will motivate that why we are doing that, and then we will look at 2 concepts. One is global alignment and second is semi global alignment, which is basically equivalent to finding an approximate occurrence of a pattern in a large text. So, let us look at this one by one. Now, in the previous lecture we were using this notion of eddy distance, that is, if there is a low cost alignment between 2 sequences, then we can say that the 2 sequences are closely related, right. So, in fact, if the eddy distance is small, then we know that the sequences are closely related. But in this lecture we are going to change this notion of distance to similarity. So, this will be defined such that, so we will define alignment scores now instead of alignment cost, and these scores will be defined such that if 2 sequences are closely related to each other, that is they are matching very well, then they will have a high alignment score. In the previous lecture they would have a low alignment cost, now they will have high alignment score. And the reason for doing this is, one, that alignment scores are more preferred than cost in biological applications, but there is also the technical reason for this, and with that we will see in the next lecture. So, let us define what alignment score means. Let us say that for any 2 characters x and y from my extended alphabet sigma union dash character, if I take any 2 characters from this set, then I will denote small s x y as the score obtained by aligning character x to character y. So, if I have alignment in which character x is aligning to character y, then the corresponding score is denoted as x s x comma y, and using this score between 2 characters I can accordingly define the score of an alignment, because if my score alignment is given by sequences u and l, again I can look at the individual columns of that alignment and I can apply this score function s to those individual columns and I can sum up the score. So, the total summation of the scores will give me the total alignment score for alignment u and l, right. So, in this case let us look at an example of a pairwise score matrix. So, a pairwise score matrix can look at like this, for example. So, suppose your alphabet sigma is ABCD as an example, and we will also include dash symbol in our extended alphabet. Now, typically a scoring matrix would reward matches. So, all the mismatches between the symbols are rewarded. For example, a match between A and A is given a reward of 1, a match between B and B is given a reward of 3, a match between C and C characters is given a reward of 2, and so on. You can also see that mismatches in this example are penalized by some cost. So, mismatches are given some penalty, and similarly if I am using dash symbol, we would typically see that there will be a penalty associated with using a dash symbol, because we are ultimately looking for an alignment where we would like to see as many matches as possible, and therefore we are rewarding matches and penalizing mismatches and insertion deletions. So, in this examples, score of aligning character C to a dash symbol is -2, Similarly, score of matching character D to character D is 3. So, this we can denote in a matrix format. Okay. So, now given this matrix, let us look at an example. So, for this alignment U and L, the alignment score will be basically the score of matching C to C, then A to A, C to B, dash to B symbol, and so on. So, if we look at using this matrix, what would be the score of this alignment? So, we can do that calculation. So, for C to C it is 2 plus then A to A, that is 1, then we have character C matching with character B. So, for that in this matrix we have -2 penalty, then we have dash to B symbol. So, for that we have -2 penalty, then D to D match, that is +3, then B to B, that is again +3, and then we are matching D to dash symbol. So, for that we have a penalty of -1. So, if we simply add these up, then we have -1, -1, -2, and this gives us 4. So, under this scoring matrix, the alignment score between sequences U and L is 4, right. So, this gives you an idea of how using a pairwise scoring matrix we can define an alignment score of any alignment. Now, based on this alignment score, we can go back to our original question, that is we will seek an alignment that achieves a maximum score. So, if we are given any two sequences A and B, again we can frame an optimization problem, that is give us an alignment that achieves maximum score. We will come back to this question in a second, but let me also address this point of how did we come up with this scoring matrix, like how are these scoring matrices typically designed. Now, in practice these scoring matrices will be designed by looking at the probability of mutation events in real data. So, for example, let us look at DNA sequence alphabet. In DNA sequences you have A, G, C and T, right. So, observe that in the DNA sequences we typically refer to a mutation from A to G or G to A as transition. Similarly, C to T and T to C is referred as transition, whereas all other mutations, that is A to C, C to A, G to C, C to G and so on, these are referred to as transversions. So, these are basically so you can see that there are 4x3 such mutations, and out of 12, 4 of these mutations are transitions and 8 are transversions. Now, in this possibility, so if you look at all possible mutations, then observe that there are 2 possible transversions, but only 1 possible transition for each character. So, for example, if you look at character A, there are you can have transversion to C and T, but you can transition to only G. So, there are more number of transversions events than transitions. But if we look at real data, then what we find is that transitions are more frequent than transversions, and that is because of the chemical structure of these nucleotides. So, if you look at the adenine and guanine, you can see that there are double ring structures, whereas cytosine and thymine are single ring structures. So, mutation from A to T is less likely than mutation from A to G, because conversion from this, because of this biochemical structure, conversion from A to G is more frequent and more easy than compared to mutation from A to T. So, these probabilities are factored into while designing these scoring matrices. So, for example, if I know that transitions are more frequent and transversions are rare, then I can accordingly penalize more for transversions and penalize less for transition events. So, while defining these scoring matrices, we will typically take into account these probability of different mutations. And similarly, you can think of now like how this is for DNA sequences, we adopt a similar procedure for protein sequences as well. Okay, so this was just a note on how these scoring matrices are developed, and in practice there are standard scoring matrices now that people typically rely on for their biological applications. So, let us go back to the global alignment problem. Now, remember that we have an alignment score defined. As I said, we can now frame a objective function that I can define similarity of two sequences A and B as the score of an alignment between A and B that achieves maximum alignment score, and the corresponding alignment can be referred to as global alignment between sequences A and B. So, that is I am looking for alignment between these two sequences that achieves maximum alignment score, and that maximum score I am referring to it as similarity between sequences A and B. So, this is now different from edit distance, because in edit distance we were minimizing the edit operations. Now, we are maximizing the alignment score. So, accordingly similarity is defined based on the maximum possible alignment score achievable between these two sequences. Okay. So, in terms of the algorithm that we need to solve this global alignment, like how do we compute this global alignment? Well, we can follow the same strategy that we did in last lecture. So, we can again go back to a dynamic programming framework where we said that we will solve a sub problem, and instead of solving the entire problem we will look at the sub problem of computing optimal alignment score between prefix of A and prefix of B. So, this is the sub problem that we are going to compute, and for solving this sub problem we have identified a recurrence relationship. So, for example, in the base case, if I am considering prefix of A against an empty string, then I would have to align all the characters of sequence A to a dash symbol. So, all the characters in this case will be aligned to a dash symbol, and accordingly I can define my base case for the recursion. Similarly, V0j will also be defined in the same way, whereas where I am aligning all the characters of sequence B to dash symbol. So, these are simple base cases, and for Vij we have the same recurrence as before, that is we have the three possibilities of the alignments, and but in the previous case we had a minimum of the three possibilities. Now, we are maximizing the alignment score. So, therefore, we will compute a maximum of all these three possibilities. So, this idea remains same as before, and again if the sequence length A is m and length of sequence B is n, then we know that the optimal alignment score is given by the last element in the dynamic programming table, that is Vmn, right. So, in this case again the time complexity remains same as before, that is if we do the recursion, the table computation and backtracking, then the complete process takes order m in time, because we are filling a table of size m cross n. So, this idea remains same as before, except that in our recursion we are solving maximization instead of minimization. Okay. So, this will give us global alignment between sequences A and B. Now, let us extend this idea and let us look at a more interesting problem where we are looking for approximate occurrence of a pattern in text. This is informally referred to as semi-global alignment as well in bioinformatics literature. So, let us look at the motivation for why we may be needing this type of problem. So, for example, let us say you have a pattern and let us say you have a text. I want to know whether there is an approximate occurrence of this pattern somewhere in the text or not. That is, if I make some small number of changes in the pattern, like maybe I may delete, insert or maybe substitute some characters, can I find a match in the text? So, in this particular example it turns out yes, there is a match. So, for example, for this pattern it is approximately matching at this location in the text. So, even though there is some mismatch, but there are many number of matches as well. So, and therefore, I am calling it as an approximate match. So, in this case, yes, there is approximate occurrence of this pattern in the text, but how do we mathematically formulate this problem? So, well, one way to formulate this problem is as following. I can say that is there a substring t dash of t, that is there a substring t dash of the text t such that the optimal alignment of the pattern p to t dash has value at least k. That is there a substring t dash. So, if I look at the entire text which is t and this is my pattern p. So, is there a substring t dash in my text t such that the optimal alignment between t dash and p has score at least k, right. So, this is the question I can ask here, because if I ask this question, then I will immediately find that there is a substring t dash right here in the text which has a very good alignment score, and this the value of k can be given by the user. So, for example, if I am solving depending on the threshold I want to tolerate, depending on how many modifications I can allow in my searching, I can accordingly set this threshold k, and based on the threshold the problem formulation will seek for an answer, that is it will look for approximate occurrence in the pattern of the pattern in the text where the alignment score is at least k. So, solving such a formulation will give us the answer to this approximate occurrence problem. The question is, how do we solve this problem, right. So, this is different from what we have solved so far. In the problem that we have seen so far, we were solving alignment of two sequences, whereas here we have to look for substrings of the text that have good alignment score. Okay. So, the next question is, how do we solve this problem? Well, one can think of a naive algorithm. Maybe what about we do brute force? We can look for all possible substrings of text t. So, I can enumerate all possible substrings and I can check for their alignment score with pattern p one by one. So, I can enumerate all possible substrings. There are n square such substrings. So, if my pattern text is of length n, then I know that there are n square substrings possible of text t. For each of these substring, I can compute a optimal alignment using the recurrence that we have seen so far. I can solve the global alignment problem and I can check whether the optimal alignment score is at least k or not, right. And if there is a approximate occurrence, then we know that at least one substring will give me an optimal alignment score which is at least k. Well, if we follow this idea, then it turns out that this idea will require n square times the time to do each alignment, that is quadratic as well. So, therefore, we will end up spending n cube times m time. So, the brute force solution of enumerating all possible substrings and trying them one by one will take n cube times m time, which may be too slow. So, it will not be practical at all. Can we find a better algorithm for solving this problem? And again the trick is to use dynamic programming, but more smartly. So, how do we find the appropriate sub problem for this problem? So, if we can find simpler sub problems that are easy to solve efficiently, then we can solve this problem efficiently. So, we have to look for sub problems carefully. So, let us understand order mn time algorithm for this problem. So, the algorithm that we are going to discuss in the next slides will only require mn time instead of n cube times m time. So, let us look at this faster algorithm. The key idea is to identify a sub problem, and in our case the sub problem that we are going to look at is we are going to solve optimal alignment score between prefix of pattern P and a substring of text T that ends at offset j. So, I will call Vij as the optimal alignment score between prefix of P ending at I and a substring of text T ending at j. So, note that I can choose any substring of T ending at j. So, for example, this Vij score here will consider the optimal alignment score between the pattern, and it can choose any substring of text T that ends at position j. So, whichever gives me higher alignment score, I will choose that. So, I am free to pick any substring. So, that is going to be my sub problem. I am going to solve for this sub problem in my dynamic programming, that is I am going to look for optimal alignment score between prefix of pattern P and a substring of text T ending at j. I can also rewrite this as, so instead of writing as substring of text ending at j, I can say that a suffix of T1 to j. So, because these substrings ending at j are actually suffixes of prefix of text T. So, these are suffixes of the prefix of text T. I can equivalently write it as, so instead of saying substring, I can write it as a suffix of text T1 to j. Okay. So, once we have this sub problem, the reason for using this sub problem is because this sub problem can be solved efficiently using recursion. So, for example, if we look at the base case, then we can start with a simpler base case of Vi comma 0, that is I am looking to align prefix of pattern to an empty substring. So, I am aligning it to an empty string. So, in that case I will have to basically in the alignment I will have to match them against the dash symbol. So, that is why I am basically summing the score of aligning each character of the pattern against the dash symbol, right. So, that is a simple base case. Similarly, if I want to define another base case of V0 comma j, then this time it will be 0, because now I am considering optimal alignment score between empty string versus a substring ending at position j, and because now I can choose a empty substring as well, that is I can choose a empty suffix of T1 to j as well, and if I choose a empty string then I do not need any alignment at all. So, I can use 0 alignment operations and I get a best alignment score as 0, because in this case using a empty string is, it will give us the best score. Otherwise, I will have to align against dash symbols which will give us negative scores, right. So, in this case, given these base cases, now we can define same recursion as before, that is Vij will be maximum of all 3 possibilities, because again if you consider this alignment between pattern P1 to I and a possibly empty suffix of T1 to j, again you can observe that the alignment can either end with a match mismatch or a insertion or a deletion, and again we have only 3 possibilities to consider. So, because we have only 3 possibilities to consider, we can define it as a maximization over all 3 possibilities and compute Vij. So, given this recurrence, you can see that this will give us a order mn time solution for solving this problem, because again this is a dynamic programming in which we are solving a table of m cross n, and each cell will take order 1 time to compute. So, now once we have computed dynamic programming table, how do we solve our original problem? So, we have let us say filled the entire dynamic programming table, we have the numerical values in the entire table. So, we have some numbers across the table. Observe that the first row will always have 0 values based on our base case, and the first column will have certain negative numbers because we are aligning pattern characters to dash symbols. So, in this case it turns out that once we have solved all the alignment values in this dynamic programming table, now we have to check is there a substring t dash of t such that the optimal alignment of p to t dash is a value at least k. Well, for that we have to basically, because the alignment is focusing on the entire string not just prefix, we have to look for the entire pattern. So, therefore, we have to look for the last row of this dynamic programming table, that is we have to check the scores of this last row and check whether we have achieved score at least k anywhere in the entire row. If we find any location where the value is at least k, then we know that there is the approximate occurrence of this pattern in the text where the global alignment score is at least k. So, suppose this value is k plus 1, then I know that there is a substring that ends at j which has a alignment score with pattern exceeding k, right. So, again summarizing this, so we have to check compute the entire DP table and we have to check the last row of the table and see if there exists any value in that last row for which the value exceeds at least k. So, this completes the algorithm, and the main claim here is that there is substring t dash of t such that the optimal alignment of p has value at least k if and only if there exists a value j such that Vmj is greater than equal to k, and this follows from theorem 11.6.2 of Gauss-Weil. So, this gives us the approximate occurrences of the pattern inside the text, and you can imagine various applications of this problem. For example, if I am doing a genome sequencing and I remember that the genome sequencing instruments will give you short fragments of the DNA, I may want to locate their approximate occurrences in the entire reference genomes and see where those fragments are coming from, and there I would want to use problem like this, that will for each fragment tell me its location in the entire genome sequence where it is approximately matching. So, this dynamic programming recursion gives you another flavor of how dynamic programming is solving us approximate pattern matching problems, and we will continue to see more problems like this in the next lecture. Thank you.